Hello all and welcome to this video. In this video we shall be discussing the first lesson on logarithms, inverting logarithmic and exponential equations. So we all know from previous years that 10 power 0 gives us 1, 10 power 1 gives us 10, 10 power 2 is 100, and so on and so forth. This is prior knowledge. I want you to observe a pattern, which is that we have 10 here in all cases, and we have a base of 10 here in all cases. We can see that this number 10 is repeating in all cases as well. For these numbers here, you can see that on the right-hand side, these are the exact same numbers. And finally, for the powers, we can see that they are exactly the same as the numbers on the right-hand side of the equation. Now, this is what we call a mathematical pattern. And all of these numbers can be verified by a calculator. So you can use your calculator to compute any of these numbers and it will yield the same result. If we have a pattern that applies to all numbers like this, we can generalize this pattern to create a rule. So instead of numbers, I'm going to take this base 10 and I'm going to call it A. And then I'm going to take these powers here and I'm going to call them B. And finally, I'm going to take these numbers here and I'm going to call them C. And then on the right-hand side, I'm going to use the same letters to represent the same numbers. So we first have log, and then the 10 we called A, so log base A. And then these big numbers with lots of zeros here, we call them C on the left. So we're going to write here C. And finally, on the right-hand side, these numbers were represented as B, so we're going to write B. So this pattern led us to our first important rule, which is that if A power B equals to C, then log C base A has to equal B. And this is the first rule that we need to know concerning logarithms. Now, we are going to use this rule to create an even more important rule. What if we decide to take the equivalent of B here, which is log base A C, and put it instead of this B over there? What do we get? So we get A to the power of log base A C equals C. Again, this here is the substitute for the letter B. So this is a very important property or feature because it tells us no matter what the values of A and C are, A to the power of log base A C equals C. In other words, we can say that A to the power of log base A would cancel out and you would just get C equals C. And this idea of canceling out is very important and we're going to discuss it in further detail in the next page. So let me take you back to some previous knowledge as well. You've all studied basic algebra and you know that if 5x equals 7, and we want to solve for x, so solving means finding x. So in order to find x, we need to isolate the x. So in order to isolate x, we need to get rid of whatever it is that is next to the x, in order to just have x on one side and the other solution on the other side. So how would we do that here? We would divide both sides by 5. And then 5 cancels out here, and we are left with x equals 7 over 5. So we found x by isolating the x, and we did that by creating some sort of change on both sides, on the left and on the right, in order to cancel out whatever is beside the x. Another quick example, if I have x plus 3 equals 9, again, I want to isolate the x, so I would subtract 3 from both sides, so these would cancel out. We get x equals 9 minus 3, which is 6. So we will extend this concept to handle a new type of equation where the unknown is the exponent itself. So if I have 2 power x, for example, equals 5, in order to find x, I need to get rid of this 2 here. And in order to get rid of this 2, I'm going to use the rule that we just said, which is that a log base a b or c equals b. And we said that this a cancels log base a, hence we get b as a final result. So how would you apply that here? If I put x as a log base 2 of 5, then this 2 cancels out with log base 2, and we do get 5 as a result. Hence, the correct answer here would be x equals log base 2 of 5. Let's take some questions to apply this concept. We have a logarithmic equation, log base 10x equals 2, and we want to figure out the value of x. So we have a base of 10, and we just said that the base of the exponent cancels out the base of the log. So the way to isolate the x here would be to have 10 to the power of the left-hand side equals 10 to the power of the right-hand side. So I'm creating some sort of change on the left and the right. They will now become powers, and on both sides, the base is going to be 10. How does that help me? Well, 10 to the power of log base 10, these cancel out together, and we get x equals 10 to the power of 2, which is 100, as per this solution here. Let's take another example. Again, I want to isolate the x, and I have a logarithmic base here of 625. So to cancel this log base, I will create a new base with the same number. So I get 625 on both sides, where the first one is to the power of log 625x, or base 625 and x. And on the right, I have 1 over 4. So this goes here, and this goes there. Now, the advantage is that these will cancel out, and you end up with x equals 625 to the power of 1 over 4. And you can use your calculator to evaluate this, and this gives us 5. A third example, we have log base 81, x equals 3 over 4. So by taking 81 as a base to both sides, I'm just going to write it as part of the equation like this. And now the equal sign goes down. So the 81 cancels the log 81, and you end up with x equals 81 to the power of 3 over 4. If you use your calculator to evaluate, you get 27 as a final answer. So the summary of this is that we always raise to the power of the base of the log. What does that mean? So whenever we have an equation with x as an unknown, we look at this base here, and we create this base on the left and on the right to the power of each side. So these are further examples that maybe you can try to solve on your own. There is nothing new here. I will move on to another scenario where the x is in the base. So for this problem here, we have log base x 25 equals 2, and we want to figure out the value of x. Again, just to simplify this equation, we can get rid of the log by raising both sides to a base of x. So in other words, we will have x to the power of log base x 25 equals x to the power of 2. These will cancel out, and we end up with 25 equals x to the power of 2. Therefore, x equals to 5. How did I get x equals 5? This is another important concept that I would like to discuss with you. So if we have 25 equals x to the power of 2, what we can do is we can take a square root on both sides, and then these cancel out, and we have x on the right, and we have 5 on the left. Another technique that would also work is if we have 25 equals x power 2, we take the reciprocal of the power on both sides. So I will raise both sides to the power of 1 over 2. Why did I choose 1 over 2? Because then the powers would cancel out, and you get x on the right, and you get 25 to the power of half on the left, and 25 to the power of half is also 5. Why do I prefer this technique of using fractions over using roots? This will become evident in the following slide. But for now, let's try some other examples. So again, the base here is x. We raise both sides to the power, to the base of x, I mean. So we have x as a base on both sides, and we cancel these out. We end up with 256 equals x power 8. I will use the fraction technique where I will just raise both sides to the power of 1 over 8, and these will cancel out, and we end up with x equals 256 to the power of 1 over 8, which gives us 2. Of course, you could have used the root as well. Here, using the root or the power are both correct. They're both easy to do. However, in the following page, like I said, there will be cases where using the root will be much harder than just flipping the fraction of the power. So for the third example here, we are solving again for x. X to the power of left equals x to the power of right. And we cancel these out. We get 81 equals x to the power of 2. And we raise both to the power of half. And we end up with these canceling out. So x equals 81 to the power of half, which gives us root 81, which gives us 9. Moving on to the final example of this lesson. These situations here are very difficult to solve with radicals. You have to use the technique of flipping the power. So let's try number 17. So x to the power of log base x 1 over 27 equals x to the power of negative 3 over 4. Now these will cancel out. So we get 1 over 27 equals x to the power of negative 3 over 4. Like I said, it would be very difficult and tedious to try to express this using a square root or a fourth root or a third root or whatever. It's much and the 3 cancels the 3, and the negative cancels the negative, and we end up with x equals 1 over 27 to the power of negative 4 over 3. And this gives us 81 at the end. Bear in mind that we do not change the sign of the power. So the power here was negative. I raised both to a negative power as well in order for the negative to cancel the negative. Let's try the second example. I'm going to raise both to a base of x, and these will cancel out. So 1 over 343 equals x to the power of negative 3 over 2. Take both sides and raise them to a power that cancels negative 3 over 2. So it will also be negative, but I'm going to flip the fraction. And this power here has to be the same as this power over there. So these cancel out, and we end up with x to the power of, just x equals 1 over 343 to the power of negative 2 over 3. And then I can evaluate this, and I get 49 as a final answer. For the final example in this video, we have log base x 1 over 4. So again, x to the power of this equals x to the power of that. These cancel out, and we end up with 1 over 4 equals x to the power of negative 1 over 3. And to get rid of the power, I will have a new power here of negative 3 over 1. And I have to imitate on the left as well. Now, these powers would cancel out, and the final answer would be x equals 1 over 4 to the power of negative 3 over 1, or just negative 3, which is 64. The last step can be performed using a calculator. And this brings us to the end of our video. I hope this has been beneficial. Thank you for watching.